Welcome to EduAspirant, our YouTube channel for academics, competitive exams and entrance exams. In the series of videos on physics, let us see what we have for you in the third and the final video on electrostatics. Electrostatics. First is electric dipole, second electric field intensity due to an electric dipole, third torque on an electric dipole, fourth work done on an electric dipole. Electric dipole. Electric dipole is a pair of equal and opposite charges separated by a very small distance. The electric field produced by a dipole is known as the dipole field. Electric dipole moment is a vector quantity and used to measure the strength of an electric dipole. As we can see in this diagram, there are two equal and opposite charges separated by a certain distance 2L. So P vector represents the dipole moment and represented as P vector is equals to Q into 2L. The magnitude of electric dipole moment is the product of magnitude of either charge and the distance between the two charges. The direction is from negative to positive charge. The SI unit of P is coulomb meter. Note, an ideal dipole is a dipole in which the charge becomes larger and larger and the separation becomes smaller and smaller. Electric field intensity due to an electric dipole. First, at a point on the axial line. As we can see in this diagram, the point P is on the axis of AB at a distance x from O. As we can see that the positive charge will repel and show the direction EB vector towards right and EA vector towards left. So the net electric field EP will be equal to EB minus EA. The vector EA vector and EB vector are collinear and opposite. Therefore, magnitude of EP vector is equals to magnitude of EB vector minus magnitude of EA vector. EA vector will be equal to 1 upon 4 pi epsilon naught Q upon x plus L whole square into I cap. EB vector is equals to 1 upon 4 pi epsilon naught Q upon x minus L whole square into I cap. Magnitude of EP vector is equals to 1 upon 4 pi epsilon naught bracket Q upon x minus L whole square minus Q upon x plus L whole square. Magnitude of EP vector is equals to 1 upon 4 pi epsilon naught 2 into Q into 2L into x upon x square minus L square whole square. Magnitude of EP vector is equals to 1 upon 4 pi epsilon naught 2px upon x square minus L square ka whole square. EP vector is equals to 1 upon 4 pi epsilon naught 2px upon x square minus L square whole square into I cap. If L is much lesser than x, then EP vector can be approximately equal to 2p upon 4 pi epsilon naught x cube. The direction of electric field intensity at a point on the axial line due to a dipole is always along the direction of the dipole moment. Electric field on the equatorial line. As we can see in this diagram, the point Q is on the equatorial line at a distance y from O. EA vector and EB vector as shown in the diagram, and the resultant of EA and EB is EQ vector, which is inclined at an angle theta from both EA and EB. Resultant of electric field intensity at point Q is EQ vector is equals to EA vector plus EB vector. The vectors EA and EB are acting at an angle 2 theta. EA vector is equals to 1 upon 4 pi epsilon naught Q upon x square plus L square into I cap. EB vector is equals to 1 upon 4 pi epsilon naught Q upon x square plus L square into I cap. As we can see in this diagram, by breaking the component, we can find that the vectors EA sin theta and EB sin theta are opposite to each other and hence cancel out. The vectors EA cos theta and EB cos theta are acting along the same direction and hence add up. Therefore, EQ is equals to EA cos theta plus EB cos theta. EQ is equals to 2 upon 4 pi epsilon naught Q upon x square plus L square into L upon x square plus L square raised to the power 1 by 2. EQ is equals to 1 upon 4 pi epsilon naught Q into 2L upon x square plus L square raised to the power 3 by 2. EQ is equals to 1 upon 4 pi epsilon naught P upon x square plus L square raised to the power 3 by 2. EQ is equals to 1 upon 4 pi epsilon naught P upon x square plus L square raised to the power 3 by 2 into minus I cap. If L is much lesser than Y, then EQ will be approximately equal to P upon 4 pi epsilon naught Y cube. The direction of electric field intensity at a point on the equatorial line due to a dipole is parallel and opposite to the direction of the dipole moment. If the observation point is far away or when the dipole is very short, then the electric field intensity at a point on the axial line is double the electric field intensity at a point on the equatorial line. If L much lesser than X and L is much lesser than Y, then EP is equals to twice of EQ. Torque on an electric dipole in a uniform electric field. As we can see in this diagram, there are two charges minus Q and plus Q placed in an electric field at an angle theta. The forces of magnitude PE act opposite to each other and hence net force acting on the dipole due to external uniform field is 0. So there is no translational motion of the dipole. However, the forces are along different lines of action and constitute a couple. Hence the dipole will rotate and experience torque. Torque is equals to electric force into perpendicular distance. T is equals to QE into 2L sin theta. Q into 2L is P, so T is equals to PE sin theta, or we can write P vector is equals to P vector cross E vector. Direction of torque is perpendicular and into the plane containing P vector and E vector. SI unit of torque is Newton meter. As we can see in this diagram, the angle theta is between P and E. This is torque P vector. Case 1, if theta is equals to 0, then torque T is equals to 0. Case 2, if theta is equals to 90 degrees, then torque T is equals to PE, which is maximum value. Case 3, if theta is equals to 180 degree, then torque T will be equal to 0. Work done on an electric dipole in a uniform electric field. When an electric dipole is placed in uniform electric field, it experiences torque and tends to align in such a way to attain stable equilibrium. As we can see in this diagram, the dipole is rotated by the forces QE and QE. Let us suppose a small angle d theta and the limit is from theta 1 to theta 2. So dW will be equal to T into d theta. Now T is equals to PE sin theta, so dW is equals to PE sin theta d theta. Now integrating it from the limit theta 1 to theta 2, we will get PE cos theta 1 minus cos theta 2, which is equal to W. If potential energy is arbitrarily taken 0 when the dipole is at 90 degree, then potential energy in the rotating the dipole and inclining it at an angle theta is potential energy U is equals to minus PE cos theta. Note, potential energy can be taken 0 arbitrarily at any position of the dipole. Case 1, if theta is equals to 0, then U is equals to minus PE, that is stable equilibrium. If theta is equals to 90, then U is equals to 0. If theta is equals to 180, then U is equals to PE, unstable equilibrium. This brings us to the end of the third and final video of the 3 videos on electrostatics. Please subscribe, like, share and do press the bell icon for updates. Best of luck for your forthcoming exams. Thank you.